Can everyone see two terminals side by side?
Yes, looks like it.
Cool. Great. So today I'll be presenting the component of the RChain platform, colloquially known as cost accounting. Some of you may know that the purpose of the cost accounting component is to limit the amount of computation that can be done in any given deploy. And this is an issue on Ethereum and RChain, similarly, because Erlang is, well, for two reasons. One, because Erlang is a Turing-complete language, which means that you can write programs that never finish running. And the second reason in relation to the first is that within the context of consensus, we have essentially, it's normal for users to deploy code that is run on other people's machines, basically. So you're running code from a Turing-complete language on a machine that's not yours. And so we have to provide some way to limit the amount of computation that can be done in a single deploy. And the way that we do that is through an economic security protocol. Basically, the idea is that upon deploying code, a user provides a certain number of units of gas, that a maximum amount that the deploy may consume. And if at any point during the execution of the program, the amount of gas has been entirely consumed, then the execution is stopped, and we proceed with the next deploy. And to guard, even against cases where users would send deploys with arbitrarily, I guess, high gas limits, we require a disincentive, I guess, for spamming the network. So there is a conversion factor that translates units of gas to units of rev. And for any deploy, the user is charged the amount of rev corresponding to the amount of gas that they give their deploy. So is everyone clear on that so far? Because it's kind of foundational.
Yes, Joe, I got a question.
Sure.
How does a person estimate how much gas they're going to have to spend before they deploy?
Good question. In the case that the deploy does not interact with any public-facing names, so those are names that are added into the registry or names that are quoted and available to everyone, such as @0, the amount of gas that a deploy consumes can be estimated by just running that code locally. And that works because in the case where you're running it locally, all of those names and the activity over those names are self-contained. So basically no data escapes because it couldn't interact with anything once it's deployed. In the case that names interact through the registry in particular, there's really the only way to estimate the amount is to run it. So I guess not so much an estimate, but yeah, I suppose that would be the simplest answer, is that if it doesn't communicate with the outside world through the registry or public names, then you can run it locally. If it does, then unfortunately you'll have to set a healthy upper bound on the contract. Does that answer your question?
Yes, thank you.
Yep, of course. So today we'll be working with the RChain testnet, which at the moment, due to the fairness constraint that we're applying, is a round-robin gossip network where 10 nodes take turns proposing deploys that are sent to them. So I guess the first thing that we're going to do is call into and listen to the logs that are generated by node 0. So the output that we're seeing right now, synchrony constraint checker, which says scene 5, means that up until this point, 5 different nodes of the network have been seen, and we require a certain minimum amount of or a certain minimum weight of the total network weight to be seen before validators before validators are allowed to look at blocks from other nodes, just to ensure that which deploys are sent are spread out in a sensible way among the nodes themselves. The network at the moment is filled with traffic that is basically one other deploy at the moment. And I'm typing in my right console window over here. The program that's being deployed is this one, new x in nothing, which is equivalent to new x in nil. So a very simple program. So if you see log output occasionally in the left side over here that shows, refunding or deploy. Oh, actually, we have an example right here. Receive, deploy, new x in empty. So that's going to be sort of the setting in which we're going to be deploying some of these contracts. Testnet has been started with an initial amount of rev provided to a specific predetermined private key, and this private key belongs to a user that we're calling Alice. Alice has a certain number of rev that, let's just say, she was provided at Genesis, and we're going to observe how Alice's account balance is modified after she runs various snippets of code. So we're listening to node 0 right now, scene 2, which means that node 3 is about up. So we're going to, let's see, I think, yes, one dot Alice deploys node, let's just give it a healthy limit, 6. In a moment, I'll show you exactly what this is doing right now. So we have, let's just see, Alice checks balance.row. So this is a source we're deploying. This is basically just a contract that's going to check Alice's account balance. So we're going to see in the side here, some of our logs being produced are going to indicate that there was an initial charge to Alice's account to pay for checking her balance. We're going to see some output indicating that her balance in her code has been run. And in fact, we see that here. And then finally, we're going to see, oh, sorry, no, I was thinking about something different. The only log output that we're going to see is this line here, which says cost accounting test, Alice deploys, balance of, this is her rev address, is 820,824 rev. Since we are listening on node 0, but we deployed to node 6, we are essentially witnessing here that node 0 has received the deploy for the balance check and has executed it or validated the deploy. Well, I guess I'll stop there. Does anyone have any questions so far? Cool. The next bit of code that we're going to run is actually a wallet creation source. So this bit of Erlang is going to introduce a new wallet, or a new rev vault with the specified, or the rev address specified here. And this rev address is going to basically represent the user, a second user, Bob, who is trying to become onboarded to the platform. So what we're going to see is that Bob's rev vault is created with an initial balance of 0, and that Alice is going to, or would ultimately be charged for creating that rev vault. So let's go ahead and run it. And node 6 should still do. Okay, deploy success. And so we will have to sit tight for just a little bit here, since we see that we're only on node 4 that's proposing at the moment. Okay, so here on the left, we see cost accounting test. Alice creates wallet for Bob, wallet, the vault at this rev address created with the balance of 0. And what we should see as a result of this is that if we check Alice's account balance again, then it would be lower than the number, I think it was, sorry, I should have even have a pen and paper over here so I can make note of this number, but I didn't. But
it was 820, 824 or something like that.
Very good, Ral. Thank you. Yeah, but in the you're right, in the range of the 800 and 30,000. So let's go ahead and run this balance check again so that we can observe this or the account deduction. So let's call here, and here we see logs indicating that our baby program has been processed and is being charged for. Right. And so here we have it again, cost accounting test, Alice deploys, balance of Alice's rev vault has been reduced to somewhere around, or 767,684, which is sort of exactly what we've been hoping for. And this way, yeah, and I guess as I mentioned earlier, this is in the spirit of providing a disincentive for Alice to spam the network by just providing computations that do not terminate. So the final bit of the demo is going to be showing basically that if a user does not have enough rev in their vault to cover the maximum possible rev that would be consumed with the deploy, that deploy is rejected. And in that sense, the rev token provides access to the decentralized compute services of the RChain platform. So in order to do this, we are going to shift, I think we're at 4. Yes, so let's go to 8. Okay, and node, let's see, what did I go to? 0? Is that what I went to? And essentially what I'm trying to demonstrate here is that since Bob's vault has been created and at this point has a balance of 0, that he shouldn't be able to execute any transactions providing his rev vault as a reference. So do we have...
Joe, which validator are you running on the left side?
I thought I was running node. Well, I guess I'm running node 8. So let's see. That would mean that. Well, I don't. Let's just go back to node 0 and see.
It's not a proper demo if something doesn't go wrong live.
Yeah, it's just that our numbering is or how we index the validators is a bit confusing because so I'm not sure if this made it in because in real life there are race conditions.
You missed.
Oh, I did. Okay, so let's just go to node
Node 4.
Yeah.
While Joe is doing that, I should just remind people that, so we've had wallet capabilities for quite some time. So we've had several demos where you can send rev from one wallet to another, but it hasn't been automatically wired into the gatekeeping of the code itself. So that's
Right.
essentially what we've done.
Okay, so do we have center 8? Here we go. Okay. And what we see on the left on node 0's logs, once Bob's code he attempts to run, which is, I believe, a balance check itself, we see in the node logs locally that when the deploy was created that Bob had insufficient funds to execute the code. This following pre-charge and refund is due to a different snippet of code. So we take that to mean that Bob's code and the effects that he desires have been successfully rejected by the network, which is, again, the first line of defense against spamming network validators. So that concludes, I believe, the functionality that we're trying to demonstrate today. So if anyone has any questions, I'd be happy to take them.
Well, I just want to thank you, Joe, for giving the demo, especially at short notice. You were not on the call when we volunteered you. So.
Yeah. Yeah.